Good morning, everyone. Thank you for taking your time to be here. So today we have another GSM talk on satellite on geodesy. So this talk will be given by Jeng Han. So he's currently a PhD candidate finishing soon at the University of New Mexico. So the title of his talk today will be Satellite Geodesy Application on Tectonic Deformation. So it'll be very interesting. So we just start. Okay.
Hi everyone, thank you again.
Just to make sure, everyone can hear us, right?
Yes.
Okay, good. Thank you.
Okay. All right. Thank you again, Harry, for organizing and setting up all this. So and this introduction, like you said, it's my final year. I'm trying to finish up. But today's talk, I'll talk a little bit more of like the methods and also like what I've done in the past and then how it relates to tectonics. So like this is one of the, if you notice, this is one of the image that we took. This is a GPS station. So we think of GPS like on our phone, but if you do a high precision, the pretty much like a disk. And then this is like a campaign GPS. You just like temporary setup, pick it up in a few days later. So this is pretty much what I do. Let's move on to the next slide. Okay. Maybe here's better. Yeah. Okay, yeah, all right. So just give a quick outline. So first we talk about what's geodesy. So, and before that, my background is, so I'm from KL. So, but I did my bachelor's undergrad in University of Maryland. So this is, if you don't know where this is pretty much Washington, DC. I just like 30 minutes away from there. And then after that, I graduated, I went to do my master's at CSUN, we call it California State Northridge. So that's in LA County. And then after that, in 2021, during COVID, I moved to Albuquerque. So this is where I'm currently at University of New Mexico. So it's been going on. Hopefully in another year, I'll be done. And I just want to say that I've actually been a member of GSM for a long time now. I've passed the student membership limit now, so I have to move on. Okay, so geodesy, very simply saying, is pretty much a study of Earth's shape. So what you have here is just, if you have the Earth, there's no solid, but just water, this is how it will look like. It will not look like a sphere, it will not look oblong, it will have like all these dips and then some high areas, because this is how it looks like based on gravity. And what geodesy is not exactly a new field. Geodesy has been here for thousands of years, and people have studied a lot, actually. So one of the story that you could learn is from Aristophanes. So what he did was he wants to measure the circumference of the Earth. So at the time he was in Alexandria, Egypt. So he hired someone to go all the way to nowadays called Aswan. At the time it's called Siam. And from there, they measured the distance, they walked, and then calculate the angle of the sunlight that came in. So with this, you have at Siam, you have this sunlight that goes down all the way, and then you could get the angle between the two cities. From there, you could get a circumference of the Earth. So this is one example of many people have tried studying the shape of the Earth, size of the Earth, and everything else. So what I want to focus is on tectonic geodesy. So as mentioned, tectonic is pretty much we know of tectonic plates, all this. So I want to study how it deforms due to all this tectonic process. So there's two examples that we know of usually, like for example, subduction zones, where one tectonic plate go under the other. So you can imagine Malaysia is here, Indonesia is right here. Indonesia is off a little bit, but this is one of the cases. There's also strike slip faults. If you know of the San Andreas fault, Sumatran fault, this is mostly horizontal movement. There's no up and down as much. So there are many ways we study tectonic geodesy in the past and currently. There's geologic. You could go out in the field, see a fault, dig a fault, and try to measure the age. Seismically, which is what Harry is doing. And then there's a lot of people doing seismic exploration, geophysics, all these things. And geomorphology, there's so many more. But in tectonic geodesy, we also could use several different methods. So one of them is GNSS, which is the GPS. So GNSS is just an umbrella term for GPS. And then the Chinese is called BeiDou, the Russian is called GLONASS, etc. We also have satellite geodesy, which is what I'm focusing on my work. I'll talk about what is the subpixel offset, and also we'll talk about what's INSAR, interferometric synthetic aperture radar, which is also my main focus. And then there's also other example of geodesy you could study with is tiltmeter, gravimeter, and magnetics, everything. There's so many more. But today I'll be focusing on these two, which is what I mostly work on. So before we get into the methods, we have to talk a little bit about earthquake cycles, like tectonics. What is tectonics? So in this case, there's a phase called interseismic. What is it? Inter, between seismic earthquakes. So what this phase is pretty much accumulating the energy. So you can imagine a spring that's being pressed constantly. So here you can imagine a spring that's horizontal, and this plate goes down. The spring is being compressed, which is the land that we stand on. And this phase is usually very long, decades to hundreds of years to even thousands of years. And I'll give some examples in a bit. There's a next phase we call cold seismic, which is earthquakes, pretty much earthquakes, the release of energy. So when you hear earthquakes, it's pretty much releasing energy. The spring is just returning to the original state, it's just after you release. So in this case, in the subduction zone, the land goes back up outside, goes back in because it was not like that before. And this happens very quickly, seconds to minutes. So example of cold seismic phase will be the 2004 Sumatra Andaman earthquake that we know of. It's one of the largest in the world. There's a lot, it's magnitude 9 and above. It's a lot of a big tsunami inundation across a whole Indian Ocean. There's a lot of life loss, and this is one of big lessons, and we are still studying about it today. So this is the figure just showing the tsunami arrival time, but you can see how far it goes on, and it keeps going on. And if you look at the seismic data, you can see the earth rings. The earth is shaking in a way. So one of the things I want to put in focus is that in this earthquake, Malaysia actually moved westwards. So there's a paper that did immediately after the earthquake. All these arrows are the GPS direction is going, and the length is the size of how much. So this is 27 centimeters. So you can imagine, if you go to Peninsular Malaysia, you can see that there's a few stations that goes about to 17 centimeters, and this is in Langkawi. So this is a big effect. This is really strong. Even Sabah was felt about 5 millimeters, which is, you could think of how far it is, thousands of kilometers away, and you could still feel it. The earth pretty much moved at that time. So what this means is that Malaysia can be affected by neighboring earthquakes. It's not just like Indonesia, but there's also the Philippines and anywhere else that we don't know of, like intraplate earthquakes that is pretty much hidden. And then another cold seismic example we know of is the 2005 Sabah earthquake in Ranau. So this earthquake was magnitude 6, about 20 kilometers deep. It's on a normal fault, which means the ground went down. And then there's one of the major impacts from this is also the landslides and the rock falls, which is secondary hazard. One of the good things that came out from this was that we did deploy, GMG also did deploy a lot of seismic stations. They managed to do all these seismic studies. And then there's also a lot of earthquake education, teaching people what to do during an earthquake, how to prepare. So all these infrastructures. And also, we also definitely know more about the seismic hazard in this area. So from this earthquake, unfortunately, life has lost, but we definitely learned a lot. Hopefully, we could prevent another incident or like reducing the risk or hazard. So the last phase of an earthquake cycle is pretty much called post-seismic. Post is after. So what this means is the earth still trying to relax. It's trying to redistribute its stress. And then it goes through these 3 different processes. It's something called afterslip. It's still slipping. Viscoelastic, the mantle, that's like hundreds of kilometers deep. Poroelastic is water, like hydrology, can still affect all this ground. So even years after earthquake, we are still affected. Another example, this study just published recently. So they did a study for the post-seismic effects from 2004 and 2005 earthquakes. We see that the deformation continues decades later. So this is 4 to 5 years before, after the earthquake of 2004 and 2005 Sumatra earthquake. Anything that's red, the ground went up. So in this case, 20 centimeters here. Anything that's blue, the ground went down. And the arrow is still pointing westwards because it's still going. It's still relaxing. So this is a lot. And it's 4 to 5 years later, even though the earthquake is gone, the ground is still moving. Even present day, Malaysia might not be really affected, but the ground we think is still moving. So this is 20 years later, and we think it could still go on for many years. Same as a lot of earthquake in Japan, 2011, we think it's still going, and this could go on to decades. So this is something we have to think of. And to better understand this process, we definitely need a lot more geodetic observations. For example, GPS. If you have more GPS like all this across the entire area, across the entire Sumatra, that would be great. That will give us a lot of information of what's happening to the ground. That we could improve our infrastructure and planning. Okay, so I'll go on to tectonic geodesy process. So in this case, I'll go with something, the co-seismic. So this is a work I've done. So one of my work I've done is in Papua New Guinea. So if you don't know where this is, so Malaysia, you can see Sabah here, Borneo. So it's pretty much east of it. So going in there, so this is a work I've published, and you could scan it if you want, take a screenshot of it. So this is published out there, 2011, 2021. So I worked with my undergrad advisor at the time in Maryland. So in this case, we studied the 2018 Papua New Guinea earthquake using a method called subpixel offset under the category of satellite geodesy. So in 2018, there's a 7.5 earthquake in Papua New Guinea. It's located in the Central Highlands, which is right here. You can see these are the shake map, meaning the closer you are to the red, the more shaking it is and the more damage you could expect. So this entire Papua New Guinea is pretty much affected. The whole country is pretty much affected. It's a thrust fault. That means the ground went up. And you can see that people were affected, 500,000 people affected. The depth we think is about 25 kilometers deep. And then we also think there's only 260 that is known. There's definitely thousands that is not known. So we definitely see a lot of landslide, which is one of the most serious in the world. You see like this, pretty much a land looks like a river, which is very, very scary. So give a little bit background of the area. So this is the elevation map. So you can see that there's a volcano here, Mount Sisa, and then there's a lot of faults everywhere across here. So it's located in a fold and thrust belt. And then in this case, there's a lot of faults and also a detachment that we know of. So in this study, like the red here is the detachment fault, which is the base of the ground. There's some faults up above. You can see that there's oil and gas. Fold and thrust belt is where we the oil and gas concentrates. So this is a lot of people done seismic studies across. And in USGS, which is the United States Geological Survey, which is one of the big research centers, what they estimated was there's a one fault model. So a fault you could imagine is a plane, a paper that's under the ground. So this fault is dipping northeast, meaning that this is the surface. You can see this here. This is a fault. This is the top of a surface, and you go down northeast direction. So it gets deeper, shallower. And there's one fault estimate. They think the fault slip about 2 meters, so which is a lot in a second, or less than a second, you can imagine. And all these stars are the aftershocks. The main shock is right here. So in this case, what we're gonna ask in our research is, can we improve our understanding of the faults? Is there really one fault that only ruptured to cause this 7.5? And how does our study compare with other methods? So pretty much these are the questions we're gonna ask, or we can ask. So subpixel offset is a method that we use. So what this means is tracks the pixels offset using a SAR image, a synthetic aperture radar. So this is a SAR image of the area. If you notice, it's black and white because this is amplitude. So 0 to 1. So that's they don't use like camera to take. They use microwave. Microwave uses microwave. But this if you take a photo, you use optical images, which is like optical wavelengths. So it's a bit different. So what this method could do is to track rapid ground changes or large ground changes. So notice there's a lot of noise around, very noisy. So that's one of the things we could track large ground movements. We use a satellite called Sentinel-1 from the European Space Agency. This is how it looks like on the space. And this method is pretty much using cross correlation. So what that means is that imagine you take a photo of you could take a selfie or whatever. You take a photo before, and then maybe 10 years later, you take another selfie. And then from there, you apply this method, you could see what has changed to you. So this is the same exact method that's working here. So you see what has changed to the ground in this case. So in our study, we found that our pixel size is about 20 meters. So each pixel, like each box is about 20 meters. And the uncertainty is 1 meter. That's because that's at least what that means is like we need to see at least 1 meter or more deformation. Like I said, it's great for large surface displacement or large ground movements. So here, what we have is 3 scenes. So scenes is just pretty much the paths or images. So here you could see this three image, they're all different. So there's two ascending, which the satellite is going up. There's a descending, the satellite is going down. So there's three different images, but we need before and after images. So we total of 6 images that we use. And the reason we use ascending and descending is because we want to constrain more than 2D. So if you only have one image, it's 1D, 2D, 3D, you need more images. So what we found was that, so this is a bit difficult to see, but east-west, north-south, and vertical. So going to focusing on the vertical, what you see that anything that's red is going upwards. Anything that's blue, like this one, is going downwards. East and so anything that's red in the east-west, anything that's red is westward. Yeah, anything is westward, and anything north-south is southwards. So what you can see that there's red and red here, meaning the fault here is going southwest. And you can see that this fault here is going, it has a red, that means it's going up. So we know that from these images that the faults are going upwards and also southwest direction. So it's pushing out this way, southwest. So I'm focusing a little bit more that you could see that in the vertical, you could tell landslides. This method is great for landslides because you could see here, landslide usually just go down. So it goes down, but it doesn't really show any in the north, south, east, west direction. So it just went down. So we know, and then compared to optical imagery, we see that this is a landslide. So this method is great for landslide and also big earthquakes. Okay, so simplifying things, just going look into the vertical displacement. So we identified there's a rupture, there's a fault surface displacement. That means what that means is if you go into the field, you could see a big wall or cliff of up to 2 meters after the earthquake. So this is big. It is 2 meters high in just a few seconds or less than a second. So this is really big movement. And then from here, we do some models. We try to simulate what is needed to generate this amount of movement on the ground. We need a fault that is about 35 kilometers long in this direction. And then here, there's another fault that's about 22 kilometers long. And uplifts about 1 meter. So if you can imagine, the earthquake happened within a minute. So everything happens in a few seconds or less. So this whole ground moved about 2 meters in a second or less. It's really, really quick. So this is a lot of movement. That's why we have so much landslides. Okay, so now you could look at, imagine, so this is why you look up from the map, like an eagle view. But if you look from the ground, a cross section, looking across in the ground, these are the 2 faults. They are dipping northwest, northeast at an angle about 5 plus, and then it extends up to 10 kilometers deep. So this is how we simulate the ground motion by using faults. And from here, so the black dots here are the data that from this map. The red lines and the blue lines are the models. So we kind of fit, that's how we know, right, this fits the best. So we think this is how it looks like. So what we use something called dislocation models from Okada. So we did a few simulations. We test 1 fault, 2 faults, 3, 4, 5. We think up in the end, we think 3 faults works the best. So 2 faults and 1 big detachment, which is the one at the base. So looking at 3D again, so this is how much it slipped on the ground. So you could see the fault slipping. The radar, it is more ground movement on the fault, not on the surface. So we think a fault moves about 5 meters on this 3 fault system. There's 1, 2, 3 faults in our study. Since then, there's also a lot of studies that do their own study. There's a study that says there's a 2 meter slip on a 4 fault system. One that says 4 meter slip on a 1 fault system with changing depth or dip. And also another one with about 4 meters on a 2 fault system with different dips. So a lot of studies are doing the same earthquake, but all come up with different results because we all use slightly different methods, slightly different modeling. But in the end, we all could agree that this is a really big landslide caused by a really big fault system. A lot of movement in this area. So going back to our questions, can we improve our modeling or our understanding of faults? Yes. We don't, and is there 1 fault, the eruption only? We don't think so. And then we could ask how, and we think our study is comparable and could be complementary to other methods. Some people use seismic studies. Some people went into the field, collect some measurements in person, which is also another way to measure all these things. So another example of this method could be used, as mentioned, is large movements like landslides. So in 2015, actually, there's a group that in Singapore, they tried to do the Sabah earthquake. they identify a lot of landslides. They did use another method called coherence mapping. So this is pretty much my work from my advisor. So what he did, you see like anything that's red, there's a lot of landslide, a lot of change to the image. So you could map all these landslides. You can see it, the entire mountain just came down, slide. So pretty much this correlates really well. So this method is really good for landslide mapping. Malaysia has a lot of landslides nowadays. So definitely this method can be done. Okay, so we talk about earthquake, co-seismic process. Now we talk about the process between the earthquakes when there's no earthquake. So in this case, this is my PhD project, a main PhD project. So in this, we are talking about the Rakhine, Bangladesh megathrust, which is megathrust is pretty much a subduction zone. You can see the plate goes down under another, and this is in Bangladesh and Myanmar. So this is our title. We just resubmit the paper. Hopefully it gets accepted this time. So it's a collaboration between a lot of people. We met in May. So that was great. And then this project is funded by NASA. So NASA has really helped in a lot of funding, which is great. So, okay, I was just skip the title. The title is very long. I'll just go straight to the topic. So subduction zones, we talk about a lot. It's actually pretty much if you remember the Pacific Rim of Fire, we don't really like to use the term, but this is pretty much, you can see, subduction zone is where it is. So Indonesia, you can see pretty much is the entire of it. There's the Himalayas, there's New Zealand, Philippines, everywhere. So they produce the largest earthquakes, and they're mostly offshore. And we all know they produce largest earthquake. They always come with a big hazard. Tsunami is definitely one of the things that we want to study on. That's why we want to study earthquakes. And one of the things that we don't really think of is, okay, so a megathrust interface where the slab, the one tectonic plate goes underneath, this is the fault. This is the base of the fault. But there are also a lot of faults up above. So we call them splay faults. So a lot of times, all this splay fault can increase hazard. So imagine this fault is moved, but you also move the other fault. So we just combine them. So the magnitude becomes bigger, the hazard becomes dangerous, even worse. So in this case, we could see that a lot of things are offshore, unfortunately. So what that means is that we don't have high resolution data. This looks very nice. This is the elevation and bathymetry data. So you could see that's the trench. This is Japan. This is the northwest of the US. They're all offshore. They are really far away, hundreds of kilometers away. It's very difficult to go put a ship. It's expensive. Logistically, it's very difficult. So what that means is that offshore trenches are very difficult to get data. We want to know how it moves, it's very difficult. But there's an interesting case where there's a sediment field subduction zone. And this is where it is. This is in Myanmar and Bangladesh area. So we call this a Rakhine Bangladesh megathrust. So zooming in, we see that this is India, Bangladesh, Myanmar, and Malaysia is right here. So you can see that there's the 2004 earthquake ruptured the area here. The earthquake was here. So if you trace along the line, actually extends possibly underneath Dhaka. So Dhaka, if you don't know, is the capital of Bangladesh. And it has implications. So the 1762 rupture that we know of from geologic studies. And this area, if this earthquake does happen, it could affect a really, really big area. Hundreds of millions of people will be affected. It's not just thousands, so it's hundreds of millions. So this is something that's what we want to really focus and study on. So in this case, we ask the question, how is strain partition is just transferred? How is the energy you could think of is transferred across the megathrust, the subduction zone, onto the fore and thrust belt, which is the things above. The megathrust, we cannot see it, but the faults above you can. So apologize for the bad font, but here imagine that the Indian plate converges with the Sunda plate at almost 5 centimeters per year. So that means the plate collides about 5 centimeters per year. So in this, what we see here is that the megathrust, people have done different studies, think that it could be inactive, 0, or it could be half as active and take up a lot of energy. So this is really big problem. This is something that we need to know. Is it active or not? And if it's active, how active it is? We don't really know. So, but we do know there are other faults like the Saigon fault is a strike slip fault, like a San Andreas is a right lateral. It takes up definitely about half of it, of the strain. And then there's also CMF, it's called Jurajampo Mao fault. Also takes up some, it's an oblique fault, which is strike slip and some dip slip component. But this is my main focus. I want to really know what the megathrust is doing. So one of the problems that we have in this area is the lack of dense GPS or GNSS. This area is about almost two times of Peninsular Malaysia. So, but we have the same amount of data as Malaysia. So what this tells is very not dense. There's not enough data to tell us a lot of small structures. Like if you're gonna see what the movement of this fault, you need a lot of GPS data beside it. We need more. We need more data here. We need more data everywhere. So why do we want to know if the fault is locked or unlocked? So what that means is that when a fault is locked, it has a potential for earthquake. So you can imagine that the spring is being compressed all the time because it's locked. If it's unlocked, that means the spring is just releasing the energy all the time. So there's not big potential of earthquake. So in this study, they did a transect across from here to here. You see that the dots are the GPS stations. So ignoring the blue, focusing on the red and the dots, the bottom here. So what this is telling how the convergence rate, which means how compressive, how much is the compression is there in terms of rates. You see the GPS data could fit two different models. So the red lines and the brown line are the model. The creep, meaning the fault is always moving. There's no earthquake potential, very, very few small earthquake potential, could also fit the same way as a locked fault. That means it could be very active or could be inactive in terms of megathrust. So this is a really big problem. So GPS, this is GPS, even though you see a lot here, but actually that's not enough. So we want to know, going back to the questions, we want to know which fault are active, pretty much, and what is the deformation mechanism, what is going on here. So what we have here is a technique called INSAR. So this INSAR, as mentioned, if you recognize this, is SAR, just now we use image with a microwave image, but we have a technique called interferometric. So SAR images give us amplitude, how bright, and phase. It looks like noise, but if you remember like oil, there's like contours. This is pretty much what we see. But what we want to measure the phase differences of the same area. So imagine, phase is pretty much wavelength of the microwave or light, anything you can imagine. So imagine you have before an earthquake, you have 1, 2, 3, almost 4 wavelengths. You take a photo, 4 wavelengths, but after an earthquake, oh wait, it becomes almost 4.5 or 5 wavelengths. Then we know the phase difference, then we could tell from that change, we know how much the ground is moving. So if you look at just the image of SAR images, you see that there's actually not a big difference, the pre-event, post-event. This is amplitude even though, but when you get the difference, you see movement, you see all these things. Zooming in, you see all these things called fringes. So imagine a contour line. If you turn on Google Terrain, if you look anything, you draw a map, you see all these contour lines. This is the same exact thing. But these contour lines are depending on the band. So in this case, depending on what satellite you use, it's 5 centimeters. So the 5 divided by 2 is to about 2.3 centimeters because the wave have to go down and come back up to the satellite. So divided by 2. So each fringe, each circle is 2 centimeters. So you add on, let's say you have 10 circles, it's 20 centimeters of movement. So this is how you calculate it or estimate it. Okay, so now going back to one of the challenges in this area, we all know that this area is close to the tropics, is very forested. You have the Magna River, always changing, so much water, so much sediments, always accumulating there. A lot of dynamic processes going on. So this brings us attention to that not every SAR images can work. Not every satellite can work. Because you see this X band, the shorter wavelength, it reflects the trees. I don't want to see the trees, I want to see the ground. C band can reflect, sometimes go down, but most of the time it reflects by the tree, leaves. L band, in fact, can actually go down all the way through the canopy and give you ground information. And this is the one that we want to see. This is the one that we want to use. So what we use is the L band satellite. So a lot of things can contribute to phase change or what we see. Earth curvature, topography, ionosphere, troposphere, noise, and ground motion, which is what we want. The rest, those are highlighted, are the things that I focus on. I try to correct for. The rest is pretty much well known. So ionosphere is one of the noise contribution. If you want to study ionosphere, this is the one you could use, but this is not what I want to see. So long wavelengths, the ions in the ionosphere is a lot. You can see all this pattern, always follow the solar, peak solar. And then you see ionosphere is up above, and then we also have troposphere, which is down below the ground. You could have stratified air column, meaning that the water vapor follows the topography of the ground. So all this can contribute to a lot of noise, which is not what I want. So my goal is to remove all this. And I could say I spent a year and a half to figure out how to remove all these things. But now going into focus, this area, this is our image area that covered. So we to technically see the trench, the megathrust. This is what we want to see, what happens at the trench, because this is the one that generates tsunami, the biggest slip of movement. So we take this satellite image from Japan, the Japanese Aerospace Agency called ALOS-2. We have almost 50 images, 49 images over 7 years. So from 2015 to 2022, we have 186 interferograms. So interferograms means a pair of image. So we have 186 pairs of images. And this figure here that you see, it looks easy, but it takes 14 days to non-stop process all these things to get you this line. Takes 14 days, and then it's a try and error to remove unanswered. That's why it takes a year and a half for me to just try to figure out what works best. And from there, unfortunately, not everything can be used. In the end, we only come about 57% that's usable. So you have to keep doing it for months to figure out what works. Why do we say it doesn't work? Because you can see there's original image, there's an atmosphere, the ionosphere image. If you subtract these two, you still get this weird pattern. What we want is to have this image so dense, ionosphere, it removes, and you can see just like, oh wow, just like one flat color scheme, not this dense. So this is an error. This is still some tropospheric ionosphere error. So if you compile those 57% of the 186 images, you get this map. So what this is, anything that's blue, meaning the ground is going down. Anything that's red, the ground is going up. So you could see that we think is going down, but I don't want to say, I don't trust a lot of information because of the river here. But you can see there's a ground that's going up, a few cities, there's a ground that's going down. So it's very interesting, but I'm not focusing on the long wavelengths because of some errors, but we can focus on the short cross sections like A here. I'll just focusing on that. So this area is called Rashipol anticline. You can see that this from 2015 to 2022, the ground is actually moving up to 2 millimeters per year, every year. So this is called creeping because it's moving all the time without an earthquake. So what this means is that this could actually reduce the hazard, or it could tell something else. We don't know. But we could see that's 2 millimeters per year. And then what we want to do next is try to model what is happening under the ground. So we did some elastic half space. If you want to know the details, it's called elastic half space. And we use some Bayesian Monte Carlo, random, just keep generating thousands of models to just try to simulate this signal. And what we simulated was this blue line. So the red line here is the profile across this area from A prime, A to A prime. The top here is the elevation. So you can see the anticline here. So this blue line is what we model. You see the blue line does not fit what we observe. Well, this model, this is how it looks like underground, the fault. It takes about 2 centimeters per year of movement. And then there's also about 2 degrees dip. It doesn't fit well. We did a test to fit this as much as we can. We need 6 centimeters of movement on the ground every year. So imagine 10 years later, you move about 60 centimeters, which is quite a lot. It's not really possible in this area. So what we see is that the best fit model does not fully fit. A fault model doesn't really fit well, and the geometry is not really possible. What proposed is an alternative model. What if instead of a fault, we actually have compression of layers, where the ground is so like a clay, like a box of clay. You press the clay, you could compress it, and then over time, it just becomes faulted because it's got more brittle over time. So we think that the ground is actually you can imagine the ground is very flexible, very easy to bend. So we think this is what is happening. When we did some simple analysis to how deep compare to how deep is the decomon, we see that our study is about 78. Other studies thinks it's 78. Our B to B prime here is about, and C to C prime is about 1 kilometer less deep, but it's close enough. We think that this method might be true. Another way you could see is how much slip is taken up by the fold. We see that, so imagine how, if you compress the ground horizontally, the ground has to go somewhere. So it goes outward. So we take this area and then you could get some estimate of rates between 1 to 3 millimeters per year. So this makes more sense compared to 20 millimeters per year or 60 millimeters per year. This 1 to 3 millimeters per year makes more, it takes about 5 to 20% of the entire budget that you have. What that means is that whatever you give, you cannot exceed whatever is given in terms of the slip rates. So it's really quick through, but we think, so going back to the question, we think there are no clear fault slip. We didn't identify any fault that is slipping, but we think there's a fault process that's going on at the fold and thrust belt. Like, so this is an example cartoon. So this is where the tectonic plate intersect. You compress the land because it's converging together. You first bend it, bend the ground, the underground. Over time, you get all these faults. So we think we might be seeing a process that's a mix between the two, but we need more studies. So this is a proposed idea, and there's a group that's going on and trying to study this, see if what we're proposing is correct. Okay, so that was pretty much my PhD, half of my PhD project. So now what I talk about very quickly is what I did for my master's and how this two project could go into the future for Malaysia. So, okay, this is Cascadia megathrust I mentioned earlier. So this is northwest of America, Portland, Oregon, Washington State, and then there's a Vancouver Island of Canada. So we hear of most people haven't heard, but we know there's a subduction offshore. And the last time it happened, an earthquake was 1700. A year 1700, so 300 years ago. So we know that this is active, and a lot of studies are being activated there. So this is, we just finished writing out. We are going to submit that soon, in a week or two. So what we have here, I was working with my master supervisor, Eileen. So at that time I was in Cal State Northridge. So what we did was we used a method called block modeling. So this is not satellite anymore, but the models. So every time we do an observation, I like to do a model. I want to know what's happening in the ground. I want to know what is happening in the future, if possible. So block modeling, you can imagine it's a block. You have faults and GPS data, combine them and connect them together into blocks. And this technique allows us to estimate fault activity from a dense block model. So in this case, in our study, what we did was we tested different subduction behaviors. So what that means is that what if the Cascadia on the megathrust is just going perpendicularly to the trench? Would that cause a sliver, a fault like a Sumatra? There's a Sumatran fault is this is Sumatra subduction zone. Or what if we allow it to slip obliquely? That means you have like it's just like at an angle. Does it just create this, or does it still create this? We don't know. We're just testing this at a time. So we have this model of the subduction slab, how it looks like on the ground. This is a surface, and this is going down. It's a big fault. And then we have a lot of GPS data. Then you can see some clockwise motion because of this subduction going on. So we combine. So what I did was we draw faults and create a block model. You connect the faults together, create all these things. So a lot of faults, hundreds of faults, connect them together, and we give them names everywhere, identify them. It's a big area, so it took us a while to connect all the faults. But the question we want to ask is, how are all these faults affected by this different subduction motion? Because this could tell us which faults are active and tell us the hazard potential. So we come up with we run thousands of models, and then we come up with a few reference models. So this is, imagine if you put this subduction perpendicularly to the trench, we get a lot more fault activation because there's a component that's missing. So the faults are more activated. They're taking out more energy, more strain to release or redistribute the strain across the country or the northwest of the country. So the blue it is the right, that means it's a right lateral fault. It's going clockwise motion. Red is left lateral, this direction. But anything that is black is inactive. Anything with a color, that means it's somewhat active. But when you allow the subduction zone or to move obliquely, we don't need a lot of faults. There's only one, you can see just one strand. That's very interesting in terms of the direction it's going. So that is very interesting. So what does this tell us? Like, so what we did next was compare with geologic studies. We have to do some comparison with other studies. So it's a little bit complicated, but I'll go through this really quickly. So the blue is the dip slip where we have a lot of faults. The red is where we have very few faults. So 0 is here, 0 is here. You can see that anything that's a value, that means it's active. The black is the geologic rates. So what people have, they go into the field, they measure how big it is, and they measure the time, everything like that. And for what you see is that we actually match our DSS, this is D, dip slip, not as well as the oblique slip. So what that means is that we think our fault the model that has a lot of faults is not does not match the real observation on the ground. So we think there's actually not as many faults that are active in this area. But like I say, we need a lot studies to continue on. So in summary, this block model method can actually tell us which faults are active, and it can tell us the rate, how active it is. And then this works better if we have more dense GPS data. So what that means is that even though we have a lot of GPS data in this area already, we still see some areas that we are not really sure, like offshore. There's no GPS data because it's underwater. We don't really have we need a lot of money to invest of an offshore network. And then the other thing we could say is that this model can help improve our seismic analysis or seismic hazard understanding by understanding active faults and how much of a fault is moving. So I actually did a model of Malaysia. So at that time, so if you notice, so this is Sunda plate, so Sunda plates, and in here, what we did, I found was that there's inconclusive results because there's not a lot of GPS stations. There's only 10 in Borneo. There's only 10 in Peninsula. For such thousands of kilometers long, we don't have enough data. You could see anything that is blue is less active. Anything that's red is more active. So you could see it's the model, as the model keeps going on, it's just Borneo is pretty much quiet. But Peninsular Malaysia, for some reason, keeps on going as active. That's an active fault. I don't think this is true because the fact that we don't have enough GPS data. So what I really want to emphasize is that we need more GPS data, more stations, and more long-term geodetic data. What that means is that we know Malaysia is a very low fault activity in terms of like, it's very slow. The faults are very slow. We need maybe 10 years long, 20 years long GPS data that's non-stop recording it. So that's one of the things that will help us improve our understanding of which faults are active, and if they're active, how much active they are they, because that is tell us how much seismic the magnitude can be. Okay. Okay. So in summary, I gave a lot of 3 different projects. It's a lot of information, but summarizing all these things is that different geodetic techniques can help complement each other, to better understand how ground moves, the tectonic earthquakes. We could possibly see the first observation of fold using satellite geodesy. So if this is true, then this could help us better identify other areas. For example, if like Cascadia or New Zealand, Indonesia, if this is true. And the other thing we could say is that this actually helps improve our understanding of subduction zone hazards. What I'm trying to do here is try and pretty much understand what is the hazard, the earthquake hazard in all these areas. And I just want to end the conclusion, this is the last slide, is that there's a lot of potential for geodetic research in Malaysia. One of the things we could definitely, I showed earlier, was analyze the fault rates, which faults are active and how active it is, because this is really important. Like, for example, 2015 Sabah earthquake, we think that it's not as active, but there's a magnitude 6, so we really want to know how the budget is. Then also, like I said, modeling deformation mechanism, 2015 Rana earthquake, there's so many different models to propose. So we could even do a better job if we have more data. And if we densify the network in Malaysia of GPSS, GNSS, or GPS network, we could actually understand how is Malaysia impacted by nearby earthquakes. We don't know. So if we have more GPS data, that will help us a lot. And I also want to say that I also do some site mass wasting analysis. So I do some, not exactly landside, but post-fire debris flows using satellite geodesy a little bit. So I've been to the field, seen a lot of different techniques that we could use with satellite geodesy, and how it can actually tells us a lot more than just earthquakes, a lot more than just mass wasting, but also how we use water, for example, groundwater, and extraction of any resources. And for that, I thank you, everyone. Thank you for attending. If you have any questions, you could definitely send me email or check out my website for any updates. Yeah, thank you.
Okay, so thank you, Jeng Han, for the very interesting talk. So now I'll open. We will have a very quick Q&A session. I think a few minutes, maybe 5 to 10 minutes, and then you can unmute your mic or you can type in the chat. And then yeah. Let me see the chat here. Maybe I'll stop sharing first.
Okay.
Okay. Let's see. Okay, so I see one question here.
Yeah, so the question was, is Instar open source and can be used by people? Yes, there is. It's actually all this, the satellite that I use is not exactly, but there's a Sentinel-1 by European Space Agency. If you look up, you should be able to download it. You should analyze it by yourself if you want. It can take time, but processing, the computer processing might take a little bit longer. But yes, everything's open source. Everybody could use the data is out there for 10 years now, and they're gonna keep continuing being open source.
Okay, that's one question. So if you have any, feel free to unmute and ask. Maybe I'll start with one.
Yeah.
I mean,
Yeah,
already
yeah.
start
Go
with
for it,
one,
yeah.
but I guess I'm very interested in the SPO and also INSAR. So based on what you studied, do you think this can be applied in Malaysia? Because we have very thick vegetation.
correct,
This is not considering the sediments and all the
Yes.
stuff. Yeah.
That's the thing. We did try. So my advisor did try with the Sabah earthquake. So we thought we could see it, but they actually couldn't see it with INSAR. So unfortunately, no. But Peaks Offset actually did a very brief analysis for if people remember, there's a debris flow in Batang Kali. So I actually did that, but the Batang Kali is too small in terms of this width. It's very small. But if you use optical imagery, you go to do pixel offset. There might be a way to see it, but I don't know how to do that yet. So, but yeah, large earthquakes, you have really big landslides, you could definitely see it. Yeah, but Instagram, it's tricky. Yeah,
Tricky.
yeah.
Okay.
Like you say, it's a vegetation.
Okay. I guess I'll just continue
Yeah,
with
yeah.
another one. So based on your study in Bangladesh, you said river affects quite a bit
Correct.
on what you're looking at. And you're saying that you're not really sure whether the subduction
Yes,
is really there.
correct.
How does river affects like your data?
So yeah, that's a good question. So actually, the river acts like, so SAR images, when you take a photo of a river or any water body, it reflects the data of it. So what you have in the river is zero data, no data. So what we have the problem in Bangladesh there is because it cuts off the image, like end of the image. So anything that's there, you don't really know if it's the same like data or same information that we have. Like the reference point is off, changes off. So river changes a lot, and then also like sediment. If a river keeps meander around, changes every year, that is a big problem. We also see a lot of what do you call farming, because people have those tall paddies, they cut it off, clear it off. We cannot see a lot of things. So that's one of the another tricky problem with anthropogenic. Yeah.
Okay.
Yeah.
Okay. So anyone else? Do you have any question? You can feel free to ask. Yeah.
Yeah.
Okay.
The one in Singapore.
Yeah.
You mentioned about you look at a few years after the earthquake and currently. So meaning the intensity becomes lesser, even though it's still happening. Can I say that?
No. No, unfortunately, no. But I know what you mean. So because we always think that you release the energy, it reduces. Yes, at that time, but earthquake or the ground is very elastic. So imagine a spring. You press a spring, you relax, it goes back to original state. But over time, it keeps pressing again. So it just keeps doing that. So we are safe now. Maybe not the same thing in 100 years. It's gonna happen again. So it's very, yeah.
For this area, is there anyone still looking at it?
Yeah, a lot. Actually, in the whole world is still actually focusing. I guess not to say surprised, but I'm still like in awe to see a lot of people still working on it.
Share it. So few hours and up to a month after the earthquake, we have
Precursor.
about
Like the precursors?
the reports of the sinkholes in.
No, I actually never heard of that.
So we have like 45 seconds.
Huh.
Yes. A few hours. Until up to 1 month.
Yeah, okay.
So that's one concern.
Yeah.
Because I could pass.
Yeah. Yeah.
So just wondering if if you say that it's not necessarily calm down.
Yes, I know. Yeah.
So I'm not pretty sure how the effect would still be in past area in contaminated.
I don't know because
Yeah.
cars is so I guess if we separate out things a bit. So cars is more like superficial. And then yeah, it could go underground because it's cave system. So I don't know how it would affect because a megathrust is hundreds of kilometers deep. But definitely water does impact things. So if we have a conduit that goes all the way tens of or hundreds of kilometers, then that's a different story. Like sea mounts, they come in, they bring in a lot of water. People think that they are either inhibit or promote slip. We don't know. I mean, we know a little bit, but every area is different. So that'll be interesting to see if you have a fault that goes all the way down. Yeah.
That happens a few hours to a few days. I understand it's something like triggered by the trend, but up to 1 month.
Yeah, 1 month is very interesting.
Yeah.
Yeah, I agree with you. Yeah. Huh, I'm not sure. Yeah. Yeah, I have to take a look. Yeah.
Okay, so anyone? If not, then we'll end the session here. I'll give 5 seconds. Okay. Now is your chance. Okay, wait.
No.
Okay. Okay, so I guess that will be it. So we would like to thank Jeng Han again for sharing very interesting work that he's doing. Hopefully everything goes well.
Yeah.
And yeah. So thank you everyone again for coming. And we'll see you again in the next session we have talked. Okay. Thank you everyone. Have a good weekend. Bye bye.